Okay, let's start. So we had started looking into trees, right? We had just started trees. We said that uh, tree, a tree is a very good, you can say ADT for sets, sorted sets, in fact. So we looked into sets, sorted sets, maps, multi-maps, and so on, right? A lot of these variants. And we said set by default is unsorted collection. If we say sorted set, that is an ordered collection. And for unsorted set, we will use hash tables. So when I say unsorted set, you can generalize it to unsorted maps and so on, right? For sorted sets and sorted maps, the best way of representation is using balanced search trees. So before we look at balanced search trees, we will first have to understand trees, and then we will look at binary search trees, and then we will move to balanced search trees. Okay, so let's start with trees. So this is one of the most powerful data structures, trees, right? So trees has a lot of applications and simple way that we use to depict family trees. This is a very generic tree, right? This is not a graph really. Parent, children relationships, family tree. Next, company organization tree. So you have a company, you have different departments and maybe sub departments there, and tiny units under those sub departments and so on. So this is also a tree way to organize any company or in general any organization. Okay, then look at all the file systems. It can be Windows or Linux or any other operating system. You see that the files are organized in the form of a tree. This is not a graph. This is a tree. So we think about this folder hierarchy, right? Folders inside folders and subfolders inside folders and so on until at the leaf level you see files, right? For example, you can have a file in the first folder itself, here itself, there can be a file, right? Or you can have folders and folders have files. This is a file. So all the rectangles that are shown in blue are files. All the rectangles that are shown in black are folders. So the folders. Folders, you can consider them as internal nodes, non-leaf nodes. So these are leaf nodes. Leaf nodes are files, right? Okay. So for all operating systems, file systems are implemented as trees. So whenever you are working with file systems, you will have to use this tree traversal algorithms and many algorithms that you use for trees. Okay, now think about a book or a web page or a research paper, right? Anything like that, or newspaper. So you have a tree way to organize information here. So you probably have chapters and sections, subsections, subsections, so on, right? This is a proper tree hierarchy. Okay, and see, one of the best ways to judge a book, right? How good a book is, you can search on, say, Amazon.com, you get hundreds of books. So you can just look at table of contents. If a book is organized very well, right? If it has rock solid organization, it means that the author really knows how to organize that a lot of information, right? So on. So organization in this tree format for books, papers, so on. Okay, now let's look at some basic terminology related to trees. So tree, it's an abstract data type that is used to store a sorted set. Okay, that's the best representation for a sorted set. Okay, so you store elements hierarchically. You know what is a parent node and child node from folders and subfolders. Root node, the starting folder, you can think, right? The top node of the tree is the root node. Siblings, children of the same parent, those are sibling nodes. These two are sibling nodes of each other. External nodes, nodes that do not have any children. So you can see the leaf nodes are external nodes. Internal nodes, non-leaf nodes are internal nodes. Ancestor node, it can be a parent or parent of a parent or parent of a parent of a parent, right? So on, that's an ancestor. And similarly, child node is a descendant or child of child is a descendant, so on up to infinity, right? Those are descendant nodes. Subtree, what is a subtree? So if you look at this tree, you can define a structure, a tree-like structure from any node being the root node, right? So you can say subtree rooted at that particular node. That's a subtree, right? So given any node, you can define a tree that consists of that node and all its children and children of their children, so on. That is descendants. Okay. Next, edge, parent child relationship, right? This is the edge. Okay. Path, it is a sequence of edges. Ordered tree, what is the difference between ordered and unordered? So here the order matters. There are some trees where order does not matter. But here, typically, whenever we look at binary search tree and other types of trees, we go for ordered trees. Ordered trees are more important for us, right? Next. So we have already discussed this. This is the root node. A is the root node. This node is the root node. A is the key, right? Maybe it might be A, the name itself, or it can be a number, 45, whatever, right? Those can be keys, the elements, the records, those can be keys. And here we are assuming that the keys are unique, okay? Because in sets, we assume that there are no duplicate elements. Then what else do we have here? So you have the edge, child nodes of A, B, and C are child nodes. You can define child nodes, parent node, siblings, D and E are siblings of B, and leaf nodes, we are right? Leaf nodes, they do not have any children. And so each of this is an edge, a collection, a sequence of these edges is a path. These two edges is a path, these two edges is a path, so on. And descendants, ancestors, internal nodes, subtree. Okay, so look at this node H, a tree that consists of that particular node and all the descendants of H is called the subtree rooted at the node H. Okay, so similarly, you can define subtree for every node in the tree. So how many subtrees are there? Same as the total number of nodes in the tree. Okay, next we define level. So root node is at level 0. All child nodes of root node are at level 1. All child nodes of root node are at level 2, and so on, right? Recursively defined. So these are the levels. The total number of levels in a tree is called the height of the tree, right? Okay, so these are some of the very basic definitions. Next, we define binary tree. What is a binary tree? Let's go for the recursive definition, right? So we said that we have an implicitly recursive data structure, right? It will be easier to see this definition. Let's see, what is a binary tree? A binary tree is defined like this. An empty tree is a binary tree. Okay, this is an empty tree, say null node, right? There is no node, right? Empty tree, no nodes. You can call this as a special node, which is null node. You don't consider this as a node. So that is a binary tree, right? Or this one. So you have a non-empty tree rooted at root node R. Suppose this is your root node R and it stores an element. So there is at least one node. Then to the left and right, you have a subtree. So this is a left subtree. This is the right subtree. Right? So what is a binary tree? An empty node, right? Empty node is a tree, is a binary tree, or there is one non-empty node, right? Non-empty node, non-null node, and it has a left subtree, that is a binary tree, and a right subtree, that is a binary tree. See, you are defining binary tree in terms of binary trees, right? So this itself is a binary tree, this itself is a binary. So then how do you define L? L is either an empty node or another non-empty node with a left and right subtrees of its own, right? So this is a recursive definition.
Professor,
Yes.
here says every node has at most 2 children. So is it possible it has only one child?
Right. So it is possible that it has only one child. In that case, see what you can do is, see, we said this is a
As now?
tree, right? R really can be null.
Okay, gotcha. Thank you.
Right? L can be null. Both can be null, or one of them can be null, right? Both can be non-null. Anything is possible because we gave this definition recursively. So this is the base case, right? This is the recursion case. The base case, you can apply it for L or R or both. Make sense? Okay. This is the recursive definition. See, this is why we had to understand about recursive algorithms, some basic understanding of recursive algorithms, right? That's why we covered recursion before trees. Okay, then decision trees. So we always do this in life, right? We take decisions. There are always a couple of decision points, and we take decision. It can be yes or no, or there can be, multiple deciding points, right? It need not be binary always. Okay, but in most cases it will be binary, yes or no. Do you want to do this or not? Right, something like that. And okay, this is real life. What about computer science applications? Are there computer science applications? Yes. See, decision tree is one of the models that is used in machine learning. So it is called decision tree model of machine learning, right? So you can use this as a model to train data to predict, right? So which other new point is inside one class or not. You can use decision. So this is one of the important machine learning models. So it is used in computer science also, right? Okay. Arithmetic expression tree. Okay, you might know this already. So what is this? Look at this arithmetic expression. For simplicity, we will have parentheses everywhere, right? For all binary operations and everything, right? To be crystal clear, there is no ambiguity here. Okay, now let's think about it. So we can represent this any arithmetic expression, right, as a tree. How? So 3 plus 1 can be written as this 3, this 1 as the nodes, and then plus. So what do you see here? These numbers or operands are the leaf nodes, and the operator is the non-leaf node, right? It is the parent of these two child nodes. Okay, what about, so this is a number, right? Once we process this 3 plus 1, we get 4 or something like that. Okay, it is some number times 3. So that some number itself is a subtree, right? The result of this computation, right? Say it is some number, that is one operand, and we have the second operand as 3. And what is the operation you are applying? Multiplication. So multiplication is here. So this is one operand, this entire subtree is one operand, and this entire subtree is another operand. That subtree can be one node or multiple nodes, doesn't matter. And then you have the operator, right? So in this way, you can similarly define all other subtrees. So you will see that this is the tree for this arithmetic expression. Here, all the internal nodes are operators. Now look at this. Let's look at the root node. What do you mean by this root node? So this is the computation you do last, right? How? This is the entire subtree on the right. First, you have to compute this. And then this is the entire subtree on the left. Once you have computed this one and this one, only then you can add the subtraction, right? So this operator is applied at the last, right? Then this is the root. And what about these operators? So these operators are applied second to last, and so on. You can recursively define this, right? The innermost parenthesized expressions are computed first. So they are at near the leaf nodes. Make sense? Okay. So that's about this arithmetic expression tree. Next, let's define some of these. Left subtree, right. Okay, you know left subtree, you know right subtree. Let's define these 3 terms: proper tree, complete tree, perfect tree, proper or full tree. So what is a proper or full tree? A tree in which every node has 0 or 2 children. Okay, so this is simple, either 0 or 2 children. If a node has only 1 child, that is not a proper tree. Simple. If a node cannot have 1 child. Okay, what about complete tree? Oh, before looking at this, let's look at perfect tree. Later, we can come to this. So what is a perfect tree? A complete tree in which the last level is completely filled. Okay, do not worry about this. So a perfect tree is something like this. A node which is fully expanded. It has all the children. So this node has all the children, right? All the children. Any tree, so which has its last level completely filled, is called a perfect tree. Completely filled. Last level should be completely filled. So if you look at this, this is level 0. How many nodes are there? 2 power 0. So this is level 1. How many nodes are there in this level? 2 power 1. So this is level 2. How many nodes are there in this level? 2 power 2. Right? So suppose this is the last level, L last. So how many nodes should be there? 2 power L last. Right? So that's the idea of a perfect tree. What about complete tree? So complete tree is something like this. So a complete tree looks something like this. The last but one level of the complete tree, right? is a perfect tree. But in the last level, the nodes are filled from left to right. There are no holes here. All the nodes in the last level should be filled from left to right. So suppose you have a tree like this, right, where a last node appears here. This is not a complete tree. See, all the nodes in the last level should appear from left to right only. What about this? And all without holes, right? Suppose you have, a tree like this. This is not a complete tree, because what about this? Right? There are holes here. There are no nodes here. Right? You cannot have holes like these. Okay. So we will see some examples. It will be easy. Now let's look at this. Is this a binary tree? The branch factor is at most 2. So yes. Is this a proper tree? This is not a proper tree. Why? Because there is a node that has only one child. Is this a complete tree? No, because some of these nodes are not filled, right? The last but one level should be completely filled. So it is incomplete, and it is not perfect, right? There's a lot of holes here, not perfect. Okay. Next, what about this tree? The branch factor is at most 2, so it is a binary tree. Is this a proper tree? Seems like, right? So there are 2 child nodes here, 2 child nodes, 2, 2, 2, 2. And here, 0 child nodes, 0, 0, 0, 0, 0, 0. So each node has either 0 or 2 child nodes, so it is a proper tree. What about complete? No, it's not complete. There are holes here, there are holes here, right? What about perfect tree? No, there are holes here, there are holes here. Make sense? Okay, what about this? Is this a binary tree? Yes. Is this a proper tree? Yes. Is this a complete tree? No. Why? In a complete tree, the last but one level should be completely filled. That is true. In the last level, the nodes should be from left to right, but here we have holes. Some of the nodes are from right to left, right? We cannot have that, right? So this is not a complete tree, and that's why it is not a perfect tree. Okay, next. If it is not a complete tree, it is definitely not a perfect tree. Okay. Next, what about this? Is this a complete tree? This is a complete tree, right? Look at this. The last but one level is completely filled, and in the last level, the nodes are from left to right. We can have holes here, that's fine. At the rightmost, we can have holes, that's fine. So this is a complete tree. Is this a proper tree? No. Why? Because there is a node which has only one child node, right? This has only one child node. Hence, it is not a proper tree. Is this a perfect tree? Definitely no. Holes here, right? Okay, what about this? Is this a binary tree? Yes. Proper tree? Yes. Complete tree? Definitely. Perfect tree? No. Holes, right? Okay. What about this? Is this a binary tree? Yes. Proper tree? Yes. Complete tree? Perfect tree. If it is a perfect tree, it should be all these things. Leaving this, it should be a proper tree. It should be a complete tree by default, right? Else you cannot get a proper tree. So if it is a perfect tree, it automatically means it is a complete tree. It automatically means it is a proper tree. If it is not a complete tree, it automatically means that it is not a perfect tree. And so what about see, these names can be different. Sometimes people use complete tree for meaning perfect tree, full tree for meaning perfect tree, so on. It totally depends on the authors. Okay. In the Goodrich book that we are following as our textbook for data structures, this is the convention and we will use it. But if we look at Anani Levitin's book, he uses a different terminology. And these are not universally accepted names, right? Because they can interchange the names. So the concepts can also get interchanged, but you need to understand what is the author's definition for that particular word. Only then you can try to solve problems in that. Okay. So do not just go by the names. So try to understand what is the author's interpretation of that word and then try to solve the problems. Okay. I mean, not just solving the problems, in general, understanding it. Okay. Next, we already looked at this. Level 0 has maximum, I mean, can have maximum 2 power 0 nodes. Level 1 can have maximum 2 power 1 nodes, right? 2 power 0, 2 power 1, 2 power 2, 2 power 3, so on. Level I can have a maximum of 2 power I nodes. Simple, right? Okay, so I will skip this. There are a couple of formulas here. It will take a lot of time to derive this. So I will skip this because we need to cover a lot of topics. So how do you implement, so say, a binary tree? There are two ways to implement this tree. See, I mean, we introduced a tree as an ADT, right? Abstract data type. So that means, I mean, what should be the functions? It can be child, say left child, right child, get element, parent, and so on. I mean, a lot of functions can be created like this for the tree ADT. How do you implement a tree? You can implement the tree in two different ways, two important ways. One is using a linked structure, using links. So think about your linked list. It was a list, but here it is not a list, but it is a linked structure using links. The second approach we will see is using arrays. So those were the two major types of data structures we looked at, when we were covering linear data structures, right? Links and arrays. So those are the two ways of implementing a tree, using linked structure, using array structure. Let's see. Suppose this is our node. Suppose this is our node. So what are all these points and links and so on? Let's take one node at a time. So this point means or holds the parent node of this node. And what about this? The left child of this node, right child of this node. Because this is a binary tree, we only have 2 pointers. But if this is a generic tree, I mean, it can hold a lot more pointers, right? But here we have 2 because it is a binary tree. So there are at most 2 children, right? Hence, at most 2 pointers for child nodes. Okay, what about this one? This is the key. This is the element. This element need not be one number. It can be a record, right? But there is a key, or there can be a key value pair. That value itself can be a huge record, so on. All that goes here, element, right? Key value pair, so on. You have the parent and you have children. Children means left child, right child. So that is what is depicted here, right? Okay, next. Oh, okay, and this one. So if there are null nodes, we can represent them using this null symbol. Okay. The second way of implementing trees is using arrays. How do you implement a tree using arrays? Let's see. So this is your binary tree, and these are the indices 0, 1, 2. Look at how we are giving the indices 0, 1, 2, 3, 4, 5, 6, 7 to 14, right? All the numbers later, so on. And suppose this is your arithmetic expression, and we gave our numbering. What is the meaning of this numbering? This is called level order numbering, right? Let's define it. So this is called level order numbering. And how do we use it to store this tree as an array? Let's see. So you give the numbering 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? Of course, there is no node here. All these are holes. Okay, but you need to include the indices or numbering for these empty nodes also. Okay, now let's look at how we store this tree as an array. In the location 0, place this symbol. In the location 1, place this symbol. In the location, say, I, place the key of the node for that for the node pointed to by I. So that's it. So that's the way we store. So you store this one, and then multiplication plus 4 minus, see, division, multiplication plus 4 minus 4 minus 2, 4 minus 2, and then what else you have? Minus 2, 3, 1, 3, 1 is here, 2 holes here, right? 2 holes. So do not store anything. Maybe you can have a special character for that, right? Null or nil or holes, right? Something like that. Next, 9, 5, 2 holes. And if there are more nodes, you can keep saving all these entries. See, this is the array structure to implement a binary tree. Okay. So this is called level numbering or level ordering, because you number these nodes level by level. You order these nodes level by level. And this is a very important formula you need to remember. Let's focus on this formula alone. F of P, right? Let's write it like this. F of okay, so I'll just instead of this one, let's look at this. Now, can you tell me what is the relationship of these child nodes 9 and 5 with respect to minus? So these are the child nodes, right? Okay, now you have 5 and its child nodes are 11 and 12. How are they related? Using, yes.
It's 2n plus 1 for left and 2n plus 2 for right.
Right. They are related using the formula 2 times 5 plus 1 is equal to 11. 2 times 5 plus 2 is equal to 12. Similarly, 5, 2 times 2 plus 1 is equal to 5. 2 times 2 plus 2 is equal to 6. So here, 2 times 3 plus 1 is equal to 7. 2 times 3 plus 2 is equal to 8. Right? So for any node, if the value here or index here is I, so what will be the indices of the child nodes? 2i plus 1. This will be 2i plus 2. Simple, right? So that's what was given using that relationship. But this is more intuitive, right? Using the example itself. Okay. Okay, next. So we looked at binary tree. Similarly, you can implement a generic tree using a linked structure. So you have the parent pointer, you have the children pointer, and you have element. Okay, this was common to binary tree also. But in binary tree, we had 2 pointers. Why do we have only 1 pointer here? This children pointer is to a list. It can be an array, it can be a list, whatever. So it can have any number of child nodes, right? Maybe it can have 2 or 4 or whatever. So you can implement this as a list, right? Array or linked list, whatever. And each of these will point to its child nodes, right? This is for a generic tree structure, but we will not look at generic trees, right? So we are focusing more on binary trees. Okay, next. Now we need to traverse or scan these trees. Now let's look at all the algorithms to do this. So there are 4 important algorithms: pre-order traversal, in-order traversal, post-order traversal, breadth first traversal. Okay, so all these 4 are available for a binary tree, but only 3, I'm not in order, is defined for a generic tree. So can you, think about why we cannot use in-order traversal for a generic tree, right? Now let's look at these types, these 4 different types of traversals. So traversal is just a scan, right? You want to scan each and every element in that tree or data set. Let's look at this. Suppose this is a root, and then you have the left subtree, right subtree. So how do you define pre-order traversal? So pre-order traversal of a tree rooted at, say, root is defined like this. If root not equal to null, see, if root is equal to null, there is nothing to scan, right? No elements to scan. Job is done, right? If root is not equal to null, what do? You first visit the root, then you visit the left subtree recursively, then you visit the right subtree recursively. That's your pre-order traversal. Done. Okay, then how do you visit this left subtree? Repeatedly apply this procedure, right? Makes sense? Recursively apply this procedure. What about in-order traversal? Simple, it's just changing these orders, that's it. You first traverse the left subtree, then you traverse the root or visit the root, right? Finally, you traverse the right subtree recursively, right? 1, 2, 3. Next, post order.
Professor.
Yes.
Can you just explain a little bit more about what does pre-order, in-order, post-order mean in this scenario?
Oh, I see. So you mean through examples or the?
No, it's just let's see here. You use this terminology. What does this mean? So, like, say, pre-order means you always visit the root first, and then left to right.
Correct. You always visit the root first.
Okay.
Root is the first priority here.
Okay. Then
right?
in order means left.
In order is from it's like visiting from left of the tree to the right. It's
Okay.
left to right, complete left to right, following this order.
Okay.
But post order is you visit the root last.
Okay. Okay.
Right?
Thank you.
I mean, we will see some examples and applications of these.
Okay.
Right? But here we will first learn the logic, right? Then we will see applications also and some examples also. Okay. So what's the difference between all these things? It is the difference in where you visit the root. Do you visit the root at first or last or in between? Right? That's the difference. I mean, we could have defined one more traversal also, right? Maybe reverse in order. How will that look like? Maybe you want to visit this first and this second and this third. Right? Okay. Next. So let's see some examples. So this is a very damn simple tree. What is the pre-order traversal? Pre-order traversal is like this. Root first, left second, right third, right? ABC. Make sense? In order is this, BAC. Post order is this, BCA. Right? Left first, right second, and the node itself, the root itself, third. Okay, so this was a simple example. What about this example? Pre-order. So visit A first, and then this left subtree, and then this right subtree. So hence we have written as left subtree of A, right subtree of A. Now let's look at left subtree of A. How do we visit this in a pre-order traversal? How do we visit this? Root first, right? Left second, right subtree third. So this left subtree of A is really BDE, right? BDE. And right subtree of A is CFG. Make sense? CFG. So this is your pre-order traversal. Okay, what about in order? Left, A, then right. So what is the in order of this left subtree? Left, A, then right. What is the in order of this left subtree? This. Right? DBE. In order of this, FCG. And then you have A. So you can apply something like this. Make sense? What about post order? So you visit left and then right and then A, right? So what about, okay, left, right. Post order of left subtree. How does that look? DEB, right? And post order of this FGC. DEB is the left subtree, right subtree traversal is FGC, and then left, right, root. Make sense? So similarly, you can solve these problems for bigger trees also. Now, look at this diagram. So this is a pre-order traversal. Root, left to right. So there are so many child nodes here, left to right. So you finish this chapter, say this chapter, and then this subtree. In this subtree, root is first, and then left to right. Okay, then you move to chapter 2. Pre-order traversal of chapter 2, you start with the root and go from left to right. Right? Similarly, 3. Chapter 3 and subtopics from left to right. And then the references. So the way in which these arrows are given, right? Those will be the order of visits to the nodes in this tree. That's pre-order traversal.
Professor,
Yes.
is there any any operation, I just want to revisit level 0, then level 1, level 2, level 3, and such.
Zero, repeat again.
Say here, in this instance, right, in this example, I visit paper first, title abstract, chapter 1, chapter 2, chapter 3 reference, then go to chapter 1, subsection 1.1, 1.2. So one level at a time from left to right.
Correct. So it is something like table of contents, right?
Yeah.
When you see table of contents. Now, can you tell me which order of traversal it uses?
It's probably pre-order, right?
Pre-order? Are you sure? Is it pre-order?
Yeah, I think it's pre-order.
Yes, it is pre-order, right?
Yeah.
Look at it. It's the same way the contents of the book or paper or anything will be arranged, right?
Yeah, my question is, I mean, is there any defined operation to do the level-wise operation? Say, I visit level 0 first?
Oh,
or
yes, we will see
Yeah.
that. We will see
Okay,
that, right?
okay,
See, we
thank you.
defined level order, ordering, numbering and all, right? We will use that
Okay.
to do level order traversal
Okay.
later, right? Okay, next. So pre-order traversal, table of contents. So as we said before, all table of contents are really pre-order traversals. Okay, so if you want to do it in post-order traversal, it looks like this, but we don't need to go over this example. Now, this is a beautiful application. Suppose you want to compute the disk space, right? Compute the size of a folder, size of a disk, right? Drive. What do you use? You use post-order traversal. Let's see. So compute disk space of root, right? Suppose you have space is equal to root.value. For each child node, let's say this is your folder. For each child node of this root, right? Space is equal to space plus recursive computation of, right? Folder 1, subfolder 2, subfolder 3, subfolder 4, and then return space.
I think this is a pre-order, right? Not post-order.
So this is post-order because, see, you have to visit this space again for the final computation.
In that sense.
Right?
Because here I see the line number 1, you visited the root, right?
Right. So visit the root means it is not the final operation on that
Okay,
root.
okay, that's okay. You use that as a
So
standard.
here it means the final operation. When is the final operation? When you know that you are done with that variable.
I got you. Thank you.
Right? The finalized value will happen when you come here. Right? So that is the post-order traversal. So it's the final operation that matters, the final value that matters. So we consider this as post-order traversal. Okay. Next, arithmetic expression. This is in-order traversal. Did we talk about it? We gave the structure, tree structure for this expression, but the evaluation of this. So if you look at this, so if you do this in-order traversal of this tree, you get this exact arithmetic expression. How? So look at this, 3 plus 1, right? 3 plus 1, that is in order, left, root, right. Then left, root, right. Then left, root, right. But this is incomplete, right? Because this is a subtree of its own. So here you will see left, root, right. That's given here, left, root, right. That's given here, right? Then, so this is complete now. So see, this is complete now. You're done with the left, huge left subtree here. Left, root, right. Make sense? So if you go in this, traverse this tree in using this in-order traversal and keep printing, you get this arithmetic expression as it is without changing the order. Okay. Now, let's talk about the concept you were mentioning. Can we do level order traversal, level by level traversal? Yes, we can do that, right? That is called breadth first search traversal, or breadth first search, or level order traversal, right? There are many names for this. Okay, so let's look at the pseudocode quickly and we will apply it on a particular example. Suppose this is the root and this is child 1, child 2, so on up till child k, right? So what do you do here? Initially, you will enqueue the root into a priority queue. You need to make use of a queue here. And you know what queue is. You have enqueue and dequeue operations. Enqueue is inserting at last. Dequeue is deleting from front. Okay. So initially you will enqueue only one node, that is root. So root is in the queue. Then you have this. While queue is not empty, repeat these operations again and again. What do? Dequeue from the queue, right? And add all the child nodes of that deleted node into the queue. I mean, after visiting the root, you visit the root or that current node, visit, and then visit root, and then include all the child nodes of that deleted node. So C1, C2, C3, C4, C5, so on, CQ. Then what do you do after this? Again, keep doing this. DQ, C1 will be out. You visit C1. That C1 is deleted. You visit C1 and add all the children of C1 to the queue. That means it will go to the end of the queue, right? Similarly, then delete C2, visit C2, add all the child nodes of C2. Delete C3, visit C3, add all child nodes of C3. So on, keep repeating this forever until the queue is empty, right? So let's take one example here. So we have one generic tree. See, you can use trees to show backtracking algorithms and so on, right? The working of recursive algorithms. They are used heavily. They are used in artificial intelligence in a concept called state diagrams, right? They are used, these kinds of trees are used in backtracking to visualize the execution of programs and so on, right? There are a lot of other applications. Okay, suppose you want to do this breadth first traversal of this recursion tree from a backtracking algorithm or whatever, right? For a tic-tac-toe application, say. Now, what do you need to do? Let's apply that logic. The queue initially is empty, right? Initially is empty. Next, you enqueue 1. So I'll just use these numbers, okay? You enqueue 1. Next, you do in a for loop. What do you do? Until queue is empty, you delete or dequeue, right? 1 is out now. You visit 1, right? So let me write the visits here, the visit order, Okay, visit order. You visit 1 and add all the child nodes of 1. So what do you have now in your queue? 2, 3, 4. Right? 2, 3, 4. Okay, now what do you do? 2, 3, 4. DQ2, visit 2, add all child nodes of 2. What are those? 5, 6. 2 is DQ'd, you added 5 and 6. Next, DQ3, visit 3, add all child nodes of 3. What are those?
7, 8, 9, and 10.
7, 8, 9, 10, 11 also, right? Now what do you do? DQ4, visit 4, and add all child nodes of 4. So what do you get? 5 to 16, correct? Now look at this order. 1, 2, 3, 4. 1, 2, 3, 4. And if you keep doing this, what order do you see? 5 to 16. Right? Because the order in which the elements are inserted into the queue are 5 to 16. So it should be 5 to 16 when you dequeue, one at a time, right? And all the child nodes will be added for the next level in the same order. So it should be 17 to whatever. Make sense? See, this is how the breadth first traversal works, or the level order traversal works. You are making use of a queue. You heavily use DQ, NQ, and all those operations, and you know how to implement a queue, right? Make sense? Okay. So we looked at 4 types of traversals, right? So you can consider, we looked at 2 types of traversals: depth first search and breadth first search. Okay. Traversals. In a tree, DFS comes in 3 varieties. You can say pre-order, in order, post order. All these are depth first search algorithms for trees. Breadth first search is level by level ordering, and there is only one order. I mean, you can also take the reverse direction. I mean, if you want something like this, these tiny variants are always possible, right? Not a big deal. Okay. That's it. Now let's move to binary search trees. So we are focusing on binary trees, okay? Generic trees is not our aim. I mean, you can always generalize it, but we will not look at generic trees. We are focusing on only binary trees. Now, one special case of binary trees is this binary search tree. What is a binary search tree? Okay, it's a proper binary tree. Now, let's think about it. It is of course a binary tree. Now let's directly look at this diagram, right? So what do you see here? Every node stores some values, right? For simplicity, we will assume that all keys are unique. There are no duplicates. We will not allow duplicates. So that's how we defined all these sets, right? There are no duplicates. Okay, so we don't need to worry about repeated elements, duplicates, and all. Okay, all the elements are unique. So we will work with these numbers, but ideally these keys can be floating point, or maybe rational numbers, or strings, characters, whatever it can be. Or it can be a collection of 2 numbers. It can be a pair. I mean, pairs of numbers also. A key can be a pair of numbers. Anyway, like, we will not complicate things. We'll take, very simple examples here. So each node stores a key. Of course, I mean, it can be a record also. Along with this, you can have a huge record or a file, right? Each node might correspond to a file also, but we will leave out all these details because you can always extend this idea. Okay, so every node has a key and we will call it as a key. Fine. Next, every node has a left subtree and right subtree. Okay, that by default is covered in that binary tree. What else is special? There is a beautiful property here. Look at this property. Binary search tree, we can call it BST. Do not confuse BST with balanced search tree. Typically, when we say binary BST, we mean binary search tree, right? If you want to mean balanced search tree, completely use it as balanced search tree. Do not short it as BST.
Maybe I suggested this just the BIST. Maybe that's easier to.
BIST, yes. But yeah, typically most books use this, right?
I understand.
Yeah, we are following that convention, but
Yes,
it's confusing. Anyway, so binary search tree. This has a beautiful property. What is that property? This property is so important. You will use this for all the functions, right? Okay, what is this beautiful property? All the numbers in the left subtree of a node are strictly less than the node value. And all the numbers in the right subtree of the node are strictly greater than the node value. Beautiful, right? And this is true for any node. Okay, what about 65? All the nodes to the, in the left subtree, not left subtree of 65 are less than 65. All nodes in the right subtree of 65 are greater than 65. So do you see this property everywhere for each and every node? It is satisfied. Okay, so this is the core property of binary search tree. And why do we say search tree? Because this property makes sure that we can easily search. How? Think about our, what was that? Binary search algorithm, right? How does binary search algorithm work? If a number is greater than some number you have seen, the mid number, you know that the number you are searching for cannot exist in the left half. You can throw it away, right? So using this property, we will apply the same ideas. Now let's see. So this is the node implemented as a class, right? Key, left pointer, right pointer, and all these basics, right? Initialization and so on. Now let's look at the search function. So how does the search function work? Suppose this is your binary search tree. You are searching for 65. And suppose 65 exists in the tree. What do? Check if 65 is less than 44.
Root?
No, it is not less than 44. Is it equal to 44? No, it is not equal to 44. Is it greater than 44? It is greater than 44. So you go to the right subtree of this node. Make sense? Now check 65, compare 65 and 88. It is to the left subtree of 88 because 65 is less than 88. If it is present, it should be present in the left subtree of 88. Next, you see that, right? The value you are searching for is same as the root value. So that's where you stop, right? And either return this node itself or return a Boolean value, something like true, false, something like that. I mean, you can implement based on the application, right? So this is how search works. If it is a successful search, suppose you're searching for a number, the number does not exist, then what? Let's see. 68. Suppose you're searching for 68. 68 is greater than 44, so go right. 68 is less than 88, go left. Greater than 65, right, left, left. And what did you hit? Your current node is a null node, right? When you recursively search for this value in the tree and you hit a null node, what does that mean? The number you are searching for does not
found.
Unsuccessful search, right? Simple. Now let's look at the code. Recursive algorithm, right? Search current. So you are given the node pointer, reference, and the target value that you are searching for. So this is the recursive algorithm. If current is equal to null, then return current. That means if the node itself is a null pointer, right, then return current. You're returning that node itself. Okay. Else if, I mean, later you can verify whether it is null or not, right? Okay. Else if the current is non-null, what do? If the target is less than current dot key, so you were searching for 65 and you have 100 here, then what do? You go left, right? If target, you're searching for 65, 65 is less than current dot key, then you go to the left. Return search in the left subtree, current dot left, target. If target is greater than current dot key, do the same on the right subtree. Search in the right subtree, target. If target matches the current key, what happens? If target is equal to current dot key, you return that node itself. Okay, make sense? So unsuccessful search, you are returning a null node. Successful search, you are returning a node that contains that value. Make sense?
Yes.
As we discuss in recursive algorithms, if possible, we should avoid writing recursive algorithms. We should go for non-recursive algorithms. So here is the non-recursive version. Search current target while current not equal to null. Okay, now directly look at what are you returning. If current equals to null, you're returning null itself, right? Okay, suppose current is not equal to null. That means it's a non-empty tree. You do the same thing. If target is less than current dot key, then your current becomes current dot left. See here, you're not calling a recursive function, right? So you need to adjust the variables itself. You need to change the values of these variables only, because you cannot recursively call anything. Current is equal to current dot left. Target is greater than current dot key, current is equal to current dot right. See, the only power you have in non-recursive or iterative algorithms is adjust those values, change those values, modify those values, right? So current is equal to current dot right. But if there is a successful search, return current. Keep doing it. At some point, right? At some point, you hit the rock bottom. Current is equal to null. What does that mean? It means unsuccessful search. So this null can represent two ideas here. Two ideas. One is the data structure itself is empty, right? The data structure itself is empty. Then how can you search? I mean, there is no element. So that's one reason you might return null. The second idea is the data structure is non-empty, but you couldn't find it, right? There were some elements in the data structure, but you couldn't find it. So this null automatically covers these two cases. Make sense?
Yes.
Now, do you see that this non-recursive version of search is better than the recursive version of search? We have already discussed about the space complexity heavily, right? We drilled into the space complexity through, in recursive algorithms. If possible, avoid recursion, because recursion implicitly uses stack space. And in the worst case, so there is a mistake here. This should be O, right? This should be O, not theta. In the worst case, right? You have to scan. In all cases, you will scan a path from root to leaf, correct? You're going from a root to leaf. This is a path. But this path can be horrible. So this height of this tree can equal n. Why? In a binary search tree, maybe a binary search tree is like this: 5, 6, 7. This is also a binary search tree, right? This is a binary search tree. You're not violating any constraints. Just that this is null, this is null. So what is the worst case height? N. Right? So if you use a recursive algorithm, very bad for space complexity. So try to go for non-recursive search, non-recursive insert, non-recursive delete, and non-recursive functions everywhere, if possible. Okay. Next, insert. So how does insert work? So search is the core function for insert and delete. We will look at insert and delete, and we are done with binary search tree. Okay. And insert and delete heavily uses search. So I will not repeat that search component again. Okay. So inserting 68, if you want to insert 68, what do? You search for 68. You search for 68. Suppose you hit a null. Then you insert 68. So does this make sense?
Yes.
Insert is same as search. Search for the element. You hit a null node, right? You have to hit a leaf node, right? Then insert it there. But of course, if 68 is already present in the tree, do not insert one more time, right? You can, don't do anything. Just stop. Why? We initially said that we cannot have duplicates in the tree. So do not insert 68 if 68 is already present in the tree. Simple, right? If it is already present, neglect. Do nothing. If it is not present, that means it leads to unsuccessful search. That means you will hit a null pointer. Insert it there. Done. Okay. So there's the logic. So insert current item. Now let's look at this. If current is equal to null, then create a node with the item that you want to insert. Okay. And that will be this current. And finally, you are returning this current. So here you are returning the new root. Okay. So here you are returning the new root. Let's see. So current is equal to new node, and you return the current. If the current is empty, then create a node, insert a node, return that node. Simple. Okay, let's see if the data structure is non-empty, what do you do? If the current is not equal to null, right, then you compare. If item is less than current.key, current.left, right? So what do you see here? This code, lines 4 to 9 is, say, 99% similar to search algorithm, right? 4 to 9 is 99% similar to search algorithm. What is the difference? The difference is here. If you already see the element, if in case of successful search, if the item already exists, don't do anything. If it does not exist, keep on recursively searching, right? Until current is equal to null. Because when current is equal to null, I mean, if you keep on searching and you're not finding any value, you will ultimately hit current is equal to null, right? So that's where you return the current. Make sense?
Yes.
Okay. See, so when current is equal to null, what happens? You are inserting here. The real insert operation is in this base case. Make sense? So this is just searching. Search. So the recursion case is majorly the searching procedure. The base case is really the insert logic. So keep searching, right? In the base case, you insert, right? So that's the fundamental logic or reasoning behind this insert function. Make sense? Questions here? Okay. So here we have a non-recursive way of solving the problem. So probably I will not cover this, right? Go over this. So how to convert a recursive algorithm into a non-recursive algorithm. Okay. I mean, there are probably many other ways of writing it, and it also depends on what you are returning. Here we are returning the new root, right? So in the other case, we are returning the inserted node. So, I mean, you can change the output depending on what you want to return. Do you want to return the inserted node? Do you want to return the new root, right? Or just, Boolean value, right? It totally depends on whatever you want. So here, I just wanted to show you that it is possible to write it in different ways, return different results, right? Okay. Analysis. Search is in the worst case n. Insert, same as search. The core logic is same as search. So worst case n, right? So delete. So I will just give a brief idea and we will go into more details in the next session. Okay. So how does delete work? So suppose, okay, instead of this, what we will do is I will show you these cases first. See, there are different cases. You want to delete a node which has a particular key, target key. There are multiple cases. What if the node is not found? What do you do? If the node is found, it has 0 non-empty children. What do you do? If the node is found, it has 1 non-empty children. What do you do? If the node is found and it has 2 non-empty children, what do you do? Right? There are 4 cases like this. So depending on these cases, the logic can be different, right? Now let's see. Let's take the case, see, this is simple, right? If the node is not found, there is nothing to be done. Do nothing. Okay. If the node is found and it has 0 non-empty children, 0 non-empty children means it is a leaf node, right? That node is a leaf node. If it is a leaf node, it is dead easy. Delete that node. Done. Right? If the node is found and it has 1 non-empty child, that's where we cover here. Suppose you want to delete 32. 32 has 1 non-empty child. What do? You just delete it. This subtree will move here. Right? It is easy. I mean, there are not many changes. Why can you do that? Now let's think about it. So you want to delete 32. You found 32 and it has only 1 non-empty child, right? Why can you delete this and replace this with the subtree, the child subtree? The reason is, yeah, go ahead.
Because you don't have a which one greater than 28 in this leaf, in this branch.
Repeat again.
So you don't have anything greater than your left child.
It's already sorted and still meets the
Yes.
requirement. I think that's what he's trying to say.
Correct. Exactly. That's the point, right? So if you look at the right child of 17, all the nodes in the right child or subtree of 17 are greater than 17. So whether you delete 32 and shift it here will not affect. Of course, it doesn't affect this subtree. It will not affect this subtree also, right? Because all the elements are still greater than 17. So the BST property is still maintained. Make sense? So you can easily delete a node that has only 1 subtree that is non-empty. If the other is empty, then it is easy, right? So what did we cover? We covered this case. Now, this requires a bit more time. I think we will cover this case in the next session. Okay, so we'll cover this in the next session. So if a node is found and it has 2 non-empty children, how do you delete that node? It is slightly complicated and we need a bit more time. So we'll take time and we will cover this. Okay. And as I said, insert and delete automatically uses the search functionality, right? You have to search whether you want to insert or delete. You have to search. So the complexity of this delete is also O of n. Okay, so we will cover this complicated function in the next session. So we will stop here. Yes, that would be the end of binary search tree. We'll cover one more function and we will complete binary search tree.